My name is Saikiran Divakaruni. Usually we call me Sai. It's a big name. What is it? One month have been working in the data science area. For that, give my background. Been doing development for years. Then got interested into this field and had the opportunity to work in it. Along with me, I have Akshayaa. She's a data scientist in our company. Next slide, please. So today's agenda, we'll just quickly look at what is visual AI. We have one simple use case that we were able to share, so we thought we'd talk about it and what kind of solution approach we took, how did we deploy it in production, and some of the benefits of it. I also want to talk about basically, so visual AI. I'm not really going to, we can what is AI the most? It's vision, digital images, videos with AI. But in the automotive space, obviously, visual AI has a lot of applications, right? Mainly in quality inspection, teardown analysis, dimensional geometric validation design, recognizing your badge scores or the OCR type, and then from end-to-end testing on your manufacturing lines, development lines, and obviously autonomous vehicles. There's a huge application there. But what I want to stress or say is there is a big difference between, because it's MCT university, I thought I will tell this. In university, you have the opportunity to do a lot of research because your professors are really looking for new things and they want to work what is coming next in the next 5 years. So you have that. But in companies, especially companies like ZF, you can do research, but generally it's not the focus. You are really solving application problems, and any problem that you are solving needs to be quick. The ROI needs to be really realized very soon. If the return on investment is going to be 5 years from now, 10 years from now, unless the company is doing really great and you have extra cash sitting around. So in that context, we wanted to just talk about a very simple use case. Although it's a small use case, we really had some impact. And just to give an idea, ZF, you must all be knowing it's one of the largest auto ancillaries or tier one suppliers, let's say. So we do a wide range of components from transmissions, chassis components, brakes, steering, and many product lines. My previous history was in brakes. So I took one of the projects from that we did a few years ago. So in this one, I'm not familiar with how a brake looks like. I have a picture there. Within a brake, you have something called a brake pad. So brake pads, how do we evaluate the quality of the brake pads? It might look very simple when you are seeing it's just a brake pad. I jokingly say this to many places because when I first met my wife, she asked me, "What do you do?" And I said, "I work on developing brake pads." And her answer was, "That's it." So that was, a shocking experience for me, but in reality, it actually told me that until you don't work in that field, you really cannot appreciate how complicated that is. Because it has, developing a brake pad is, it has its own challenges and it's a very interesting. So in that, the shim plays a very major role. The reason why we have shims is basically to reduce noise and vibration. And the way we come up with the solution are different types of adhesives, different types of shim materials, composite materials. It's a very interesting subject. So in that, what happens is if your bond quality is not good, your shim can debond during testing, during usage. And we had this manual method of this grid template that you could see. Nothing wrong with that, but there are two things in that. One is it's a very time-consuming thing, and it's also very subjective. So if I look at it, I can come up with one answer. At the same time, another person can look at it and give you a little different answer. So we definitely had a lot of inconsistencies there. In the past, before we had this compute power and before we had, AI and machine learning, not that much visible. We tried many methods, used MATLAB coding, we tried many open source images, software, VBA, a lot of stuff, but we never were able to get to a really good model or what do you call a reliable model that could do this for us. Obviously, when we had this AI thing open up and much more accessible and cheaper, we said, yeah, we got to really utilize visual AI here. So next slide, just to give a context, how much time, what is the process here, right? I'll put a picture here. Once the shim is debonded, an engineer has to really take it, place this grid, mark the areas that are not bonded well, come up with this calculation, and then say that the bond is good or bad. And as you know, engineers can spend their time in more useful stuff rather than doing this repetitive manual work. So we said this is an application where we would use AI. The solution approach we took was, okay, let's use this deep learning technique, CNN, and we came up with 3 approaches. One is classification. First, we need to classify if it is good or bad. Then we need to predict the score. Like we had a requirement of 90% or above is a pass, 90% or below is a fail. And so we came up with a regression model to give the predictive score. And then segmentation. The segmentation was mainly used to identify good or bad. And this is again one application where Akshayaa did this project. So I want to hand over for the technical details.
Hello, everyone. My name is Akshayaa. I work as a data scientist with the analytics team at CRF, and we're mostly work on IT-related projects. My background is also computer science, and I was a data engineer in the past, and now I'm a data scientist with my exposure towards data. I've been working with. So moving on to the solution approach. So we used a simple image classification, a CNN model, because as soon as we met Sai, we knew there was a camera set up in our lab that was capturing these manual shims. And immediately we knew that this could be that we could create a solution through CNN and try to see how well a neural network can identify a good or bad image. And the image in picture would technically look like this. That you see here, that's the input image that we had to pass. And for an IT person, for a non-business or non-technical person from the engineering side, it was very difficult for us to visually see and identify if it is good or bad. So it was something that we had to send it to the a model and then understand how it was, detecting good or bad coverage. So this is a simple CNN workflow textbook version, just passing in the first step is our pre-processing of the images, and we made sure that it is 256 by 256 pixel, and we made sure we had a color image because that's something we started with. We still explored it with a grayscale image and found how the accuracy behaved, but that I come to it later. And the first approach that we started with was when Sai explained us about the shim. He mentioned how they see it today manually. And they told us that this part is something that they need to ignore every time when they calculate in the manual version. And these are all the red spots that's actually just telling us that there is some bad coverage there. And the green part was a good coverage. So we had to manually data label this as the first approach, because when someone from the engineering team told us this is how they do it today, that's the approach that we wanted to go with and see how the model would behave if we send it with a manual data labeling process. And we achieved like an 80% accuracy with our CNN model with the feature extraction I've just put together here to showcase how the model architecture is. It was a convolutional neural network, and we have multiple layers. And in that, we have 256 filters and 188 filters. So that way we can hierarchically get more visual features, and we flattened it from 3D to 1D, and the basic CNN architecture is what we followed here. And when we reached the accuracy, the test accuracy as 91%, we're still not satisfied with it. And there was a lot of manual labeling that was required in this procedure. Even though we had Azure ML as a backup where we can use that for data labeling, we still felt that there was a lot of manual intervention there. And we tried to pass the original image. This is the original image that we would get. This is a simple picture that is being taken through a good phone or just a digital camera in a lab environment. So that's the image that we got, and we sent it as an original image and not unannotated version, and we achieved a 100% test accuracy. And we wanted to see if it is really 100% test accuracy because we were not sure how to validate our model's result. So we used a GradCam to visualize where the CNN was exactly focusing to see if it was focusing in this area where exactly the good coverage is shown. Like there are some adhesives that you can see which are actually telling us that this is a good coverage, and the lesser adhesives you see, it's a bad coverage. So we wanted to see exactly visually how the CNN has, identified that this is a good or a bad coverage. And for that, we used GradCam, and we saw that the prediction was accurate. It did not capture any of the other, other target areas. It was only targeting the adhesive part. So we felt that the model has performed pretty well, and this was the result. We only had a very small set of data set that was like 74 images initially we got. We had already labeled it good and bad coverage, and we used TensorFlow and Keras to infer the labels when we were creating the model. So the trains and the validation split had 45 in the training set and 29 in the test set, where we achieved like 100% accuracy on the 29 images. And also to further validate it, after the GradCam exploration was done, we had another 35 or 40 images, which was completely unseen by the model, and we got still 100% accuracy on that. So we were pretty much happy how the image classification worked. I think one second. Okay, I think the order is changed. Okay. So we were pretty much happy how the classification model turned out, and we also wanted to further see or further get the granularity of the image, because like in the manual version, they were able to calculate a specific score. So we already had a historical data where images were already provided a manual score by engineers or testers who were testing the particular film. So we use that historical data for our regression model. We use the same CNN approach and architecture, and okay, so I'll just explain the regression part, but this was the image classification result we had. And then moving on, we had a regression model, which is very similar, but it was technically calculating a score, not like a binary classification. It was calculating a numerical value, a quantitative assessment. So this is how we got the image. We already had an actual score, a simple regression model to just help us understand if this type of image was already, if it already had this type of a score, then how well is the regression model predicting a score for a new image that it has not seen before. That's something that we did just to get a quantitative assessment on this topic, and the linear regression graph and a scatter plot just to see how well the model performed. We are actually, sorry, we're missing a slide which had more information about the accuracy score of the regression model, but we had like an 85% accuracy on the regression model. And we understood from the scatter plot that the model was mostly predicting all the scores that were on the higher level and not on the mean values. So we wanted to make sure that we have more data sets available or more data available for the regression model to be more accurate. That's something that we had to conclude when it came to the regression model. And like Sai mentioned in the beginning, there's also image segmentation. That's something that we explored because we knew that we had to manually annotate the shims, which were time consuming. So we used the Azure ML and used a pre-trained model like Mask or CNN, and we trained the image segmentation. We trained the model with the same set of images, but they were annotated using Coco, which had more XY coordinates, and we wanted to see if the model is seeing the edges or if the coordinates matter for the model to detect good and bad coverage. This is more for the qualitative analysis that we did. This was at the very initial stage when we had the annotated version for our classification model. We wanted to see if we can better annotate the shim bond. Are we getting a better result? That was the approach we wanted to have for the image segmentation. So we did this completely using Azure ML and trained Mask R CNN model. So in this case, we still achieved a 60% accuracy, which is even lesser than our manually annotated CNN classification model. So we decided that this may not be a good approach to move forward. We would rather have our own model deployed to production because we had a good result and the consistency was managed with new or unseen images for the end result. And this is how the image segmentation results look like in Azure ML. So this is basically, since we use Azure ML, it is simply you put data in the cloud and then there is a model that we train automatically and then maybe hyperparameter tuning, and we can actually just send it to a REST endpoint, which can directly showcase the results like this. So we wanted to also check if this might be a good approach to specifically detect where a bad coverage is and a good coverage is. So that was our initial idea, and we would be further exploring on this topic to see with more data. But at this point, we decided we will stick with the classification of the regression model for our production environment because that fetched more accurate results and we were able to satisfy the business demand. So moving forward, this is a simple data labeling technique that we used because this is, like I mentioned, it was the manual version, and this is an automated or more precise version that we used in the Azure platform. And moving on to the best practices that we followed, because we are partnered with the Microsoft, we predominantly use Azure related products, and our development environment is also Databricks. So with Databricks, we have this ML flow for our ML ops, which is very helpful, and we use this from the beginning for our models evaluation. So every time we wanted to tune our hyperparameters or validate what was the learning rate in a regression model and see how well, how the learning rate, when we change the learning rate, how well the model performed, and that was helpful for us to choose the parameters that we were using. So we predominantly used ML flow, and data quality is the first thing that we addressed in the image pre-processing state, where we did the basic steps: cropping, resizing, adjusting the brightness, and also making the image to a certain pixel so that it is throughout balanced and it can capture final details of the images for the data. And also we normalize the data at the initial stage. This is all the basic stuffs we covered without the second thought. That's all like textbook version. We followed every step. And the data labeling part, I've already talked about this. And we also, the test and validation part, we made sure we used the GradCam to test that and prove that the CNN model has accurately predicted the results and not just randomized. So that was one, and these are all just few best practices that we followed. Moving forward, deploying this in production. That was the more time consuming part, because when it comes to the model development and understanding the data, it just took a week or so. But the deploying part was the most tricky part. And we had other teams in helping us because we already have a computer vision toolbox in our organization. We wanted to reuse the existing solution. We did not want to create a user interface for just the use case. We wanted to reuse what was existing within the organization. And when it comes to computer vision toolbox, we have multiple ways of deploying it today in our organization. And one is the edge IoT devices that's in the plant, where you can actually use for capturing the images as it comes. But we wanted, in our case, we wanted something that will be deployed on cloud, because this is going to be for testing and the quality team to have access to a user interface where they can just upload an image and then they can get a result. If it's good coverage, what is the percentage? And if it's a bad coverage, what is the percentage of the coverage? And like Sai mentioned, the percentage of coverage needs to be at least 90%. They already have a threshold. So if it is lesser than 90, they would have that immediate chance to look at it and say why it is lesser than 90. And if they have to, they can immediately send it for further validation. So that way it's a lot of, you don't have to sit and they don't have to like manually look at it and spend 1 hour or 2 hours on trying to get the result. They can just get it on the click. So that's the aim we had for this. So the data management part, that is a little bit time consuming, because we had to collect all the data that is already available. It was earlier not available in cloud. So we had to first migrate all the data to our cloud storage. And we created a Flask API where we can upload these images and using a metadata format, so that we have a metadata and the image, everything needs to be mapped together, mapped exactly right. And then the Fast API would upload the images. And once the images are uploaded, we also, in the same script, we had the models packaged as a H5 file. And then we were able to run a scoring script to display the image in the user interface and the result of the qualitative assessment. That's basically the binary classification, good or bad. And then the quantitative assessment, that's the specific score from the regression model. So that was something that was displayed using the script. And also we provided it as a wheel file, bundled all this packaged all this as a bundle and provided it as a wheel file. So if someone wants to use it on the desktop, they can just install the model. And also the user interface, we had, that's something that I just mentioned. So it's end of the day, it's a user interface. You have a image that you have uploaded for any type of vehicle or any type of shim. This is also, it can be sent from any region as well, because it's in cloud. Anyone from any of the quality team can have access to it, and they can just upload the file and they'll be able to click on the image and see what's the result of that particular shim. And for monitoring and retraining, we used MLflow, like I mentioned before. And also for retraining the model, we are using a feedback loop where the user would actually tell us if it is really good or bad coverage. And if they find it to be different than what they expected by just looking at it, because of their experience of working with a shim before, they would be able to provide us a feedback, and then we would continuously loop it to retrain the model with the new set of images. So this is the full overall vision of the technical part. And this is the overall end-to-end AI pipeline that we developed. This is a quick solution that we wanted to provide that will be helpful for the team to click and get their results rather than manually trying to find a solution. Thank you.
I thought that,
I'm sorry.
well, I thought that after we finish this technical portion, it's also important that we give you the business case, because this is what our management really wants. I mean, they're happy about the technical portion, but in the end, they always keep asking about what did I save? I mean, how much did I save? And what is my ROI, right? So in this specific case, like Akshay was saying, the engineering team finds it really useful. We can actually show about 14.5% FTE saving. FTE means full-time engineer saving. So they don't need to spend time analyzing this, and they can use that time for something useful. So that kind of equates to about $65,000 a year, around 65,000. It's a small amount for the company size, but if you take the department, it's a huge saving. It's a very huge saving. And like Akshay mentioned, in the past, the data in our US location, Koblenz location, or in Germany, China, India, they were all doing this and they had it in their SharePoints. There is no common cloud where you could actually learn from each other. By doing this and deploying this, everybody had access to every region. In the past, you need to ask and they can send you, but you don't know whom to ask, which project to ask, and it's always not easy. The biggest thing is the manual method took about 10 to 15 minutes, depending on the engineer, depending on the shim, but AI was like almost like each image can be analyzed in 0.1 seconds. So you got 100% productivity, right? And the another big thing is in our manufacturing, where whenever they have a failure, they think that a batch came and they had a failure, they had to remove the shim and they had to send it to engineering. Our plant, in this case, was in Mexico, and it took 2 to 3 days for them to send the pads here. We analyze it, and the shipment will be sitting in the inventory. It's a lot of waste of time. And with this, they are able to take a decision instantly. They don't even need to contact us. So there was a lot of benefits by doing this. And next slide, please. So with this, what we thought was, okay, how can we scale this? And we have this model now. We have deployed it. How can we really use this for different applications? So we are now currently working on, I have listed a few of them here. We are working on using a similar approach for teardown analysis, for identifying a test failure as it happens, and then sorting out many images within our teardown analysis projects. So if one team could save about 14.5%, and we could scale this at the divisional level, you could see more savings. And if you really scale it company-wide, then I mean the amount of saving you really see is really great. Next slide, please. So what I want to conclude is, before Visual AI goes and finds the ghost, right? I saw this on LinkedIn and I was like, oh, it has to be there. So let's utilize it and try to do some practical stuff, because when Visual AI is here, I think it will be a problem. With that, I really thank you all. Thanks. Thank you, Voxel 51 and the MCT for giving us the opportunity. And I was the one who screwed up that one slide that Akshay was going to say. Sorry. Thank you. And any questions? Here's the update.
So you mentioned the CVT, that's from network Simulink or from other?
Well, it's, I mean, maybe they have the same CPT name, but it's an in-house developed computer vision toolbox developed within ZF. It's a ZF developed application.
Also that developed by your guys?
Yes.
Okay.
Yes.
Yes.
We named it CVT, so maybe the CVT is a common name everyone uses. Yeah.
Yeah, so earlier in slides, you mentioned that you got a 100% testing accuracy. Well, I believe that is mostly because of the 40% dropout, but did you apply any cross validation for it? Because the test set is really small.
Yes, that's a good question. We wanted to do that, but at that stage, we were also trying to get more data, because this is not, like I mentioned, this is not just for the 75 images, because people, like from anywhere, people are going to keep uploading. We're improving our storage, the capacity of the images. So the more data we get, we'll be able to determine that. But we did not do the cross-validation at that point because this was strictly a 2-week project kind of a situation. So we did as much as we could, and we wanted to deploy it so people can actually, store their images and use the model. That way we'll do that when the retraining and all that comes into picture.
And also we get more feedback, right? So after that, we actually did a few more images with a different type of shims. We still got 100% accuracy. But again, like Akshayaa said, we wanted more. And when people start using and give the feedback, then we can retrain that.
And the type of images are also very different. They're not exactly like how I showed in this particular presentation. They could have a different background.
Yeah,
They could be
instead of black shim.
yes. And they could also be taken, it could have been taken on a carpet. So we don't know. The background really matters. So we experimented a little bit by changing the background, blurring the background, and grayscaling the background. So we wanted to see how the model will perform for such scenarios as well. And the model pretty much gave us the similar results, but like I mentioned, more data, we can explore it further.
Thank you.
When you gave the model to your user teams and they gave you feedback, what was the, I guess, like biggest reason, or you found the biggest reason for like the model performance that you fail or weaker?
I guess I can say because I had some of my feedback from the teams, it was mainly the background. So initially I was very surprised with the way the images were being analyzed by the model because I thought maybe we need to like use this digital camera in a certain format. Pixels accurately, it really did not need that. It was just as long as the picture was clear. Take it with the cell phone, it was okay. But then the background really made some difference in the result. So yeah, I think even you tried making it black and white, and that actually showed, right? So that was one of the examples we tried. So background was critical. So as long as we tried to have a similar background, the results were, for the most part, pretty accurate. We hardly got any negative results so far. But somebody said, "Oh, it's totally off."
Yeah.
But we didn't get it yet.
So when you guys did the visualization of your features, do you have any visualizations or like do you have any insight into what you look like when you did unstructured unlabeled data?
Sorry.
So you said you guys did a visualization of the what features the combinational network was looking at. Do you have any idea? Like, what, yeah, the right.
Yes.
Do you have any idea of what the features that were actually what? And what did that mean?
I don't have an image exactly how it looked, but we just had
I think that maybe even let me see if I understand your question correctly. The things that was mainly it was looking at was the what do you call the image when you have the light source, the how it is reflecting basically, and then wherever there was this. When you say it's an adhesive basically, it's a glue. Let's say to put it in simple terms, how much the glue was disturbed. That's really what it was looking at. The reflectivity, if it is really reflecting, it means it's not bonded. If the glue is disturbed, it means it's bonded either on the shim or on the back. I think that's what it
to visualize using the diagram, we just used a color code to
Yes,
understand
to
how.
make-
Yes, yeah, just a heat map. That was the word I was looking for. I'm sorry.
Why not use the drag model directly? Why you got put efforts in the trying version?
Cost.
First.
I'm thinking.
And our work for we use the drag model. We want to do credit house.
But this is also a little bit specialized, I think. You really have to see, I mean, identifying that, I don't know, we didn't try that or maybe tried, but
We started with the CNN and it did provide the results that we were looking for. Like I mentioned, there's time constraint, there's cost constraint. And there's also deployment. So we already have an environment set up, but we just wanted to have a model that was already established. So we tried to reuse what was available.
No, it's actually those base model pretty much advanced, right? But multi-models for everything. So we just inject vector database and pick it up. Whatever the results for in seconds. If you use like certain documents and everything, quite important to bring ourselves. Not like.
Well, I think that is, I would say this last year and this year is where it got really popular.
That was 3 years back.
It's a little old project, and at the time I would still say, so, okay, yeah, starting maybe.
Did you see what's the impact of rotation images? The images seem to be all in the kind of one particular orientation, right?
Yes.
Have
We
you
made
seen what's the
sure-
impact of rotation there?
So, yes.
Skew and rotation, if you have, does it mess up your model?
Yes, it does mess up our model. That's why we had to rotate it to a certain, so we made sure that we had that balanced rotation. It did mess up the model, I think. I don't exactly remember what the score was, but that's how we started, working with, we did explore that as well.
I expect never to happen.
Yeah, that happened at the first, level, and then we had to make sure we crop, resize, rotate, and also check how well the image is. We had to make sure they were balanced, so.
But you also have a very small data size.
Like
One of the
I
things
mentioned,
actually
we
for your
started with a small data set because it was all on a SharePoint and a lot of teams were involved. We had to collect all of them, so we have now converted it to cloud, so.
We have now, the last we started using it, we have now more data sets and more, but when we started, anyways. But the surprising thing was, as a user of how I see it manually, the experts were like, we were pretty happy with the results. And then we said, okay, let's start using it. And like I said, I hardly had any negative results. It was doing pretty well.
Yes, so you mentioned that it was very time costly and also the data set was very small. And you mentioned that it was making some sort of difference in performance when you augment the what are the other augmentation methods that you have tried in order to make it more variable? Since it seems like the model was more like underfitting, since the data is supposed to way too small as well.
So it was underfitting when we were manually annotating the images, but it was not underfitting when we just shared the original version of the images. But like we mentioned, when we did this experimentation of the project, we only had a certain type of images. Now that we are uploading more images, and there were even the background, we had only like a small set of images that had a different background. So we tried to use the data augmentation technique and see if that made a difference. And the small data set with a different background did change the result. And then we had to, yeah, that might have, I don't exactly remember if it caused underfitting, but the underfitting only caused when we passed the manually annotated images. Not
When we allowed the model to learn by itself, I don't think the data was list. I mean, we didn't see that when we.
or maybe I'm not getting a question again. Maybe you can.
No, I was just wondering what other augmentation methods that you have tried in the rather than augmenting the background.
It's the only thing that we because of the image capacity that we had at that time. That's all.
Would it like using high resolution images would help the model better to kind of generalize to different kind of data set? It's like, especially when you do the augmentation as well, since it effectively results. But using higher resolution images.
Yes, that is, so we initially wanted higher resolution images, but that's how much of a higher resolution images they were able
No,
to.
but I can add that because I don't think that it really made a difference. That's what I was telling, right? I was thinking that we really needed a high resolution image and everything. As long as the image was clear, we pretty much got the results. I mean, pretty good results. We didn't. It should not be shaky, obviously, those kind of things. But I don't think a very high resolution image versus a camera image, picture taken with the camera had a difference because we tried this. We got the images even from the suppliers. We uploaded it here because every supplier has this quality process where they have this digital camera, parts come through, they will take the picture. So it's all very well regulated, so good pictures, right? So it didn't really make a big difference.
I mean, I just thought about that because like I kind of have kind of small data set, like 74 images. So it's thing would balance the other side. So to have a better resolution with a low small data set, or the other way around. Yeah. Especially that you're dealing with kind of tiny objects to data.
Yeah,
So yeah, I was curious.
possible, but like I said, we have been, initially when we released this, we were very cautious, right? We were looking, we had engineers confirm it. Now now I would say we have a lot of data that has retrained. Hardly we had like, one was the background, but the other one I could say is when we had a shiny shim, where the shim itself is a metallic shim, there's no rubber, and it was very reflective. Then obviously we had, but again, I think we retrained a few things there, and now we find it good now.
So you guys said you tested the binary classification versus the regression problem. What was the performance of the regression versus binary? I think you discussed the accuracy there.
It was not binary versus the regression. Regression was pretty much to get to get the granularity of the shim itself, like to get a score.
Yeah.
So for the regression model, I think the accuracy was around 87%. That's the slide that we missed actually.
Yeah.
Yeah. So it was around 87%. I showed the scatter plot where we were able to see that it was mostly predicting all the scores that were above 90%. But we wanted to make sure we wanted more data for that model to perform better. That's the conclusion we had point.